Okay, this is section 2.2. So now we finally get to an interesting topic, limits for functions that are not single-valued functions, not functions from R to R. So maybe hopefully you've studied calculus before, and maybe you've encountered the so-called epsilon delta definition of limits, which is we're not going to spend time on that. We're going to be a little bit less precise and just use a kind of intuitive idea of what we mean by limits. So the single variable calculus notation for a limit looks something like this. And what this means is that we have a function f, and we're thinking about what happens to that function, meaning if you're thinking of the graph, it means what happens to the height of the function, or the y value. But if it's the graph, we could say it's the height. So what happens to this function as we choose values for the input, as the input x variable gets closer and closer to some value? And we use this to understand functions that might have some kind of problem or some kind of unusual behavior. So suppose we have some picture like this. So first thing, I'm saying this is a function, but we should ask, is this actually a function? So for it to be a function, remember that if you draw a vertical line anywhere, you should only cut the curve in one place. And that's true here. If I draw a vertical line here, I'll only cut it in one place. If I draw a vertical line here, I'll only cut it in one place. And if I draw a vertical line at A, I only cut it in one place. What is meant by this circle? What are we trying to convey by drawing such a circle? We're just trying to say that the height of this function is not b, it's c. So we can have, that's still a function, but we draw a circle here to say that the height is not b, it is c. We put a dot here to mean that it is c. So first of all, we should make sure that we agree that this is a function, and then we can say, well, what is f of a? And we just said f of a is not b, it's c. Okay, so on the other hand, a limit might be interesting here. We might ask, let me use this here instead of having to write this out. So what is the limit of this function as x gets close to a? So that does not ask what is the value at exactly a. We already know that, and we already said that the value at a is c, but that's not what this question is asking. So this question is saying, if you just got very close to a, what would you guess that the height of a at a was? Not what is it actually, but what would you guess if you could only look at values that got closer and closer to a? So you certainly wouldn't guess c then. You wouldn't, if you didn't know exactly what was happening at a, you would never guess that the height was c. You would guess that it was b. So we say that the limit for this picture over here as x approaches a is b. So the value is c at a, but the limit as x gets closer to a is what you would guess if you only could check values close to a but not at a. So it's trying to describe the pattern that's happening near a, even if what actually happens at a doesn't fit into that pattern. So some functions have this kind of strange scenario. So in that case, the limit is an interesting tool that can explain what's going on near a, as opposed to at a. Now, if you just have a normal function, say, like that, and at a, then here asking the question about the limit is not so interesting, because it's the same as the actual value. Here, f of a is equal to b, and the limit is also b, so it's not so interesting in this case. You can still ask the question, you can still answer the question. But here is where it's kind of interesting, because the limit is not equal to what the actual value is. And you could actually have a function like this. Let me just, I can't erase this very easily, but just suppose I erase this. There's nothing here. So you just had this picture with the circle there. So even that is still a function because it passes the vertical line test, but the domain of this function, we could say that A is not in the domain because the function has a circle there, means it's not defined there. So A is actually not in the domain, but you could still ask what's the limit as you get close to A. So even then it's kind of an interesting or useful tool. And of course, in that case, we'd still say the limit is B. So anyway, this is the idea of limits. Now later on we're going to talk about continuous functions. And this, naturally we would call this kind of continuous, like it's kind of smooth, nothing, nice and smooth. But this function, suppose I had that dot back here again, up here. So I don't think you would call this, you would want to label this as continuous with this picture, right? So continuous means basically you can draw the function without taking the pencil off of the paper. So this one you can do that, but here, if you want to draw this function, you have to take the pencil off to draw this part up here. So this would not be called continuous, and this would be. And if we didn't have this and we didn't have this, that also would not be called continuous, just if you just had this, a circle, and then here. So we'll want to talk about continuous functions, and that's basically what we mean by continuous functions. Now we're not referring to the epsilon delta rigorous definition of limit. We're just giving these intuitive ideas based on these kinds of pictures. So anyway, this is a function. These pictures are functions from R to R, and we've seen this before. She says this idea generalizes immediately to functions from Rn to Rm. So we could write, so if we're talking about a function into Rm, then we have to write it bold. And if it's the elements of the domain of the function is Rn, then we have to write the x as bold also. And then we say, well, as x gets close to A, now this A has to be a vector, just like x is a vector, so the vector x, and it's best not to think of this in terms of arrows, vectors as arrows, but think of them as ordered n-tuples, like this is an ordered n-tuple. The input is n, so we call it an n-tuple. So it would have n elements in it here. And that is getting close to some A. A is also in Rn, so it's also some n-tuple. And when we say this vector is getting close to this vector, we just mean that the elements of this vector are getting close to the elements of this vector. So we have elements, so we have commas here, and then the same number of commas here, because it's the same space. They're both in Rn. So this element here is getting close to this element here. That is, if we write this, we mean that this element is getting close to this element, and the next element is getting close to this element, and the last element is getting close to the last element. So all of the elements here are getting close to all of the elements here. That's what we mean by this. So if this was in 3 space, so we might have x1, or we could call it x and y and z, but I'll call it x1, x2, and x3. So that's x, that's the vector x in R3, and it's getting close to some A, which is also should be in R3. So maybe the A is equal to, it's an actual constant, so it's like It's not just variables. It's like, say, some 3, 4, 2. So we can say what happens as this gets close to that. So this is, we could think of these as points in R3. So this point is getting close to this point. So, and so we say, if, so this would be the input of some function, right? And the input is getting close to this value, and then we're saying what happens to the output of the function. What does it get close to? So the output in this case is in Rm, and so it's going to be a point in Rm that it gets close to, and we call that L, whatever point in Rm that it gets close to. So she says this idea generalizes immediately to functions f from Rn to R. In particular, by writing this equation, where f is like this, we mean that we can make the vector. Now, why does she call this a vector? Because this is the output of this function. So it's going to be in here. That's a vector. So this vector in here gets arbitrarily close to some vector, which we'll call the limit vector, L, by keeping the vector x sufficiently close to, so that's just like here, by getting close to A, but not at A. We don't care what happens at A, and A could jump way up here, but that's not what we're interested in. We're just saying as we get close to A. So here, it's when this vector x gets close to this vector A, and that's in this sense that we set up here. So it gets close to, but not equal to A. The word close, so what do we mean by x gets close to A? It means that the distance between x and A is getting smaller. A is fixed, so x is moving closer to A, and so the distance between them is getting smaller. So the word close means that the distance between f of x, remember that's going to be in Rm, so that's some vector or some point in Rm. So the distance between that and the actual limit, so it's like the b when it's just in R, is small. The distance is small. Thus we offer a first definition of limit using the notation for distance. So what is the notation for distance? When we're talking about vectors, it's the norm, right? This means distance. So we're going to use that here. So this is an intuitive definition, so we're not using epsilons and deltas, and we're not going to do that, epsilon and delta, at all. You can read it yourself, but we're not going to talk about it here. So so what does this mean? So this is in the case where we have some function from Rn to Rm, say, means that we can make the value get as close as we want to some point L. This is the point L, actually. We can say that it's a vector. We can say that it's a point. Whatever we say, it's in Rm. So we can get the output to be as close to that as we want by keeping our point x close to A, by keeping the point in Rn close to A, also in Rn, but not 0. We don't care what happens when x equals A, just when it's close to A. Now, okay, that was general. That's for any Rn to any Rm. If we can take a special case where we're taking Rn into R, so that would be a scalar valued function. So we don't have a bold F here. In that case, what do we mean by length? So this is the length this norm here is the norm in Rm, because these are, this norm here is the norm in Rm because these are in Rm. This is the norm in Rn because these are in Rn. So if we're talking about, this is R1, right? So then what's the norm in R1? That's just the absolute value. So we can switch this to absolute value. So we can write this. So in the case of a scalar valued function, that means this is just R1. The vector length, this, can be replaced with just the absolute value. Similarly, if f is a function of just one variable, then this can be replaced by that. So in that sense, that this is a more general definition than the single variable, than the function of a single variable. What should I say? The scalar function of a single variable is just a particular case of this more general definition. So here's a picture. This is just in a scalar valued function of a single variable, just like the picture I drew up above. So we can say, what's the limit? What's the limit as we get close to 1? Okay, this is a little more problematic than the function that I wrote up here, because as we get close to a on this side, the height is getting close to b, and here as we get close to a on this side, the height is also approaching b, but that's not happening over here. As we get close to 1 from this side, the height is always 0, right? Well, this is the function, and its height is 0. So, but on the other hand, as we get close to 1 from this side, the height is always up here, which is 2. So that's different than this one where they were coming, if you came from this side and this side, you got the same thing. So in this case, remember from your calculus class that we say the limit doesn't exist, whereas this case, we say the limit does exist, it's equal to b. So what's a way to write a formula for this? This is a way to write a formula for that, because this just says whenever x is above 1, the value of f, the value of the function, is 2. So that says whenever here, that's this part here, if x is above 1, the value is 2. If x is less than 1, the value is 0. And you can notice where the equal sign is and is not. But let's just read through what she says, because it's going to be useful when we consider functions like this. So she says the graph of f is shown here. What should the limit as x approaches 1 here be? She says the limit can't be 0. So we might think it's 0 because the height here is 0. But on the other hand, no matter how near we make x to 1, no matter how small we take x minus 1 to be, in other words, the distance between some x and 1, the values of x, and we mean that the values of x can be both slightly larger and slightly smaller. So it could be here, but it also could be here, or here, or here. So the values of f corresponding to those values of x, so the ones that are larger than 1, when we do over here, the value of f is 2. But when we take these values, the value of f is 0. Thus, for such values of x, we cannot make this arbitrarily small. So we might say that the limit is 0, but if we come over from this distance, we can't make the distance between the actual height, which is up here 2, and 0 arbitrarily small. It's always the distance is always, as long as we're to the right of 1, if we postulate that the limit is 0, we have to be able to make the height of the function the distance of the height of the function n0 be as small as we want, but we can't. Okay, I'm not going to push that. It's a little bit hard to see, but hopefully you know this. Okay, so let's look at this example. So here we're talking about a function from R2 to R2. So what is it? It's just going to be this. 5. So whatever x is, we're just going to multiply that x by the scalar 5. Okay? So she says then it should be obvious intuitively that if x approaches some vector in R2, so it's going to be, so that is our A. Now it's written in kind of an annoying way. Maybe I'd prefer to write it like this. 1, 1. It should be in R2, and 1, 1 is the same as I plus j. So it's some vector in R2. You might prefer to write it like this, or maybe you prefer to write it like that. Somehow this seems easier to understand for me. So this is A, which is clearly in R2. So anyway, as x approaches some A, and here's our function f, then the limit as we get close to A of 5x is just going to be, so what happens as, so what does this function do? This function here, what does it do? It takes whatever x we put in. Remember, x is on R2, so we could call it x1, y1, or I'm sorry, x1, x2, or we could call it x, y, but I'll use x1, x2. So what does f do to this, to the input? It just multiplies it by 5x, which means that what? It means we get 5x1, 5x2. So if we're getting close to this vector, or we write it like this, 1, 1. So what happens when we put that in to our function? Our function multiplies this value by, if this is our function, if this is the input, then if we're multiplying it by 5, then what? We multiply each element by 5. So if we're getting close to 1, 1, then clearly the output is going to be getting closer to 5, 5. Or we can rewrite 5, 5 as 5i plus 5j. You can either write it as 5, 5, or you can write it like this, 5i plus 5j. Okay, so how can we write this out a little bit more explicitly? So remember, x is in R2, so we'll write it as, again, I would write it this way, but they're writing it this way. So xi plus yj, could just write it as x, y. So if we write x this way, then we want to show that the limit is this, which means that we can get as close to this as we want by making x as small as possible. By making the distance of x from I plus j as small as possible. So let's see what that means. So we've considered the distance of f from what we propose the limit to be, which is 5i plus 5j. So here we consider that distance, which is, this is the way we would write that distance. Then we can expand this. So f of x means 5x means, if this is x, then we would say it's 5x I plus 5yj. Again, I wouldn't write it that way, but we can write it that way. Minus 5i plus 5j is the proposed limit. Again, I wouldn't write it that way, but we can write it that way. So this is the distance. We can rewrite that like this. And then what do? They combine the I terms and they combine the j terms. And then this is the norm. So that means that we should take the dot product and then the square root. So the dot product means take this times itself plus this times itself. So that's this times itself is 25, x minus 1 squared. That's what we have here. This times itself is 25 times y minus 1 squared. We have that. We have to take the square root. So that's equal. We can pull out the 5 in the square roots from, pull it, the 25's become 5 out here. So we get that. So we want to show that this distance can be made as small as possible. That's what we mean by saying that this will approach this. So that means we want to show that this can be made as small as possible. And what as small as possible as when? When x approaches this value. So they say that x minus this distance, equals this. So if we keep this small, can we make this small? And that's obvious. If we make this small, we can also make this small. So therefore, we finally can say that the limit of this is equal to that. Okay, it's a little bit messy. I hope that you can follow it all. But I think the most interesting part is just to say that what does this mean? It means as x, which is in R2, gets close to something else in R2, that there's a limit which is going to be in R2, because this is also R2. Okay, next we're going to do the same thing here, but from Rn to Rn, and it's going to be very similar. And then we're going to do it even more generally. So this was from Rn to Rn, and we had specifically a 3 here, but we're also going to do it from Rn to Rn, but not with a specific value of 3, but for a general value of k. And we're going to say that if h is equal to kx, then the limit as x approaches a of h of x is ka. That's similar to what we got here. The limit was 5. This was our a, so it was 5a. And here, we're going to say this is our a, so it's going to be k times our a. So this is a more general expression of what we showed up here. In fact, maybe we won't go through this. We'll just say that this is going to be a general rule, which is if our function is just a scalar times x, then the limit is just going to be the scalar times the a. But basically, it means that just like in the case of functions of a single variable, a scalar valued function of a single variable, that you can just, if you're doing a limit, you can just put in a into here, which means put a into here, and you get the limit. So you just get k times a. Okay, let's stop here, and we'll come back and continue